I think I'm just going to use the board today since it's a shorter lecture anyway. And we're going to spend most of the day working on an in-class assignment. That'll also be what we're finishing up tomorrow. Some more practice with word problems, some more practice with conversions, and starting to involve atoms and elements into our word problems and conversions as well. So we'll start while we're getting those printed. We'll start by talking about atomic mass a little bit more. We ended talking about atomic mass and how we have a conversion for 1 AMU. Does anybody remember what AMU stands for? Atomic mass unit. Anybody remember what the conversion is? Close. On the conversion sheet, it actually has an AMU to kilograms. I think it's 1.6 times 10 to the minus, what did we decide, 27? Yeah. Kilograms is 1 AMU. That's an absurdly small number, right? We ended talking about how big of a number a mole is. This is 1 kilogram divided by a mole. So it's going to be 0.26 zeros and then a 1. It's an absurdly small mass. So we don't actually measure in things like this. We actually count atoms and we count nuclei in terms of moles. And so the reason that this is a convenient conversion is because if you take this and you convert this kilograms to grams and you multiply by Avogadro's number, that mole number, 6 times 10 to the 23rd, what you find out is basically 1 AMU is equal to 1 gram per mole. And really, this is 1 AMU per atom is equal to 1 gram per mole. So basically, we have a definition of an AMU for talking about individual atoms. Physicists like to do it like that sometimes. Physicists also have a weird energy unit called an electron volt. That is the amount of energy that you get from a single electron being passed through 1 volt of potential difference. That's, again, not useful number because it's just way too tiny to actually ever be measured. So for the most part, when we actually look at these atomic mass, we're going to be thinking about atomic mass in terms of grams per mole. So if we looked at, say, our argon over there, it's 39.948. That's the atomic mass of argon. And what that means is basically if you have 1 atom of argon, on average, that atom's going to weigh 39.948 AMU. But it also means that if you have a mole of atoms, it's going to weigh 39.948 grams. Which means we've got a combined unit here, and we're going to be able to use this as conversions. This is going to be the #1 way that we're going to get back and forth between a number we can measure, because we can measure grams of something pretty easily, right? But the atomic theory says that it doesn't matter how many grams we have, it matters how many atoms we have and what ratio the atoms are connected in. So this is going to be our #1 way that we convert between something we can measure and something that where the chemistry is actually going to make sense, right? So this is going to be a really important conversion. And for the most part, we're not going to use AMU per atom. I want you to know that it exists. It's on the conversion sheet so that you can use it if you ever needed to. But in this class, especially, actually, I don't think in any of my classes do I ever actually ask anybody to calculate anything in AMU. It's just not a useful value. Grams per mole, on the other hand, is. All right, so if we're looking at this argon atom, it's got a mass of 39.948 grams per mole, or 39.948 AMU. What does that tell us about how many subatomic particles we have in that argon nucleus or in that argon atom? So let's say we're talking about an argon atom. It's neutral. What are our 3 subatomic particles that we care about? Protons, neutrons, and electrons. Are there more than that? Maybe. Has anybody heard of anything smaller than protons, neutrons, and electrons? Quarks. Yeah, quarks are actually a subatomic particle. Protons and neutrons are made up of quarks. Take 3 quarks, and I always mix up which way it goes. It's either 2 up quarks and a down quark is a proton, or it's 2 down quarks and an up quark is a proton, and the other one is a neutron. Basically, that's just getting even smaller. But then we're getting into like the particle accelerator range. We're not actually going to be able to ever see free quarks floating around by themselves. So for the most part, we're only going to look at protons, neutrons, and electrons. Fun if you want to get an idea of just how strange scientists can be when they're naming things, especially in the 60s, you should look at the different types of quarks that there are. There's 6 types of quarks that we've discovered, but they don't call them types, they call them flavors. There's 6 flavors of quarks. There's up quarks and down quarks, and I think left quarks, and there's no right quarks, but there's a strange quark and a charm quark, and there's some other really weird name. Basically, physicists in the 60s must have been just high when they were naming stuff, because I have no idea why else they would name things that weird. So if you want to read about the smallest things that we know about currently, read the Wikipedia article on what's called the Standard Model. The Standard Model of Physics basically it's like a smaller periodic table. It's like 4 by 6, and those are all the smallest particles that we know and how they interact with the 4 major forces. And the Wikipedia article is a decent introduction to it if you want to know more about that. It's not something I ever took a class on or studied, so I don't know a whole lot about it. And I believe quarks are on there, those 6 of the 24 fundamental particles. All right, so back to where we were talking about argon. How many of every subatomic particle do we have in a neutral argon atom? How many protons do we have in argon? And how do we know that? Because it's the atomic number, right? All you have to do is look at the periodic table and you can find that one. How many electrons does it have if it's neutral? Also 18, right? If it's neutral, that means you have to have the same number of protons and electrons so that they cancel out. How many neutrons does it have? Say that again. In this one. 40 minus 18. Basically, with all of our subatomic particles, we're going to treat the electrons like they have a mass of 0, because within sig figs they do. They're so small. And we're going to treat all of your protons and your neutrons like they have the same mass. They just have a mass of 1 AMU. It's really like 1.007 AMU for a proton and 1.008 AMU for a neutron. But it's close enough within sig figs. We're just going to say round it to the nearest 1 and count them like it's an integer, because it is an integer number of protons. So how do we get from number of protons and the mass to neutrons? You round and subtract. Basically, protons plus neutrons has to add up to 40. So if we have 18 protons, we've got 22 neutrons. How much of this is review? I mean, not from Monday, but from previous science classes you've had. You seen all this before? Cool. No? Well, let's add something that you probably haven't seen. Look at the periodic table for chlorine right next to argon. What's the atomic mass of chlorine? 35.45. What do we do with that? That's not really close to 35 or 36. How do we know how many neutrons are in it? Short answer is we don't really know. This is actually an average of two possibilities. Turns out the atomic masses that are on the periodic table, I was hedging on this earlier and I said, this is on average, I would say on average, your mass is going to be this. Because some elements on Earth are actually, they have more than one isotope that's commonly found, right? And an isotope is kind of like an ion, except for neutrons. An ion meant that we had a mismatch between the number of protons and electrons. An isotope just means that we have a specific number of neutrons. So in this case, we actually were looking specifically at argon 40 is going to have 18 protons and 22 neutrons, but there are other isotopes of argon that don't have a mass of 39.9. Right? Maybe not on Earth. On Earth, I believe the argon only has one common isotope, commonly found in nature anyway. But chlorine, on the other hand, actually has two common isotopes that you can find, which is why its atomic mass is nowhere near either of them, really, because it's actually the average. If you took 100 chlorine atoms, on average, their mass is going to be 35.45 AMU. But that's because it's a mixture of chlorine 35 and chlorine 37. Right? And the way we write that, if we're writing the symbol for that, we'd write your atomic symbol. Remember, we put charge up and to the right. The mass number goes up and to the left. So you can have chlorine 35, or you can have chlorine 37. They're identical in pretty much every way, with the exception of their mass. They have the same number of protons because they're both chlorine. They have the same number of electrons because they're both neutral, and they have the same number of protons. But they don't have the same number of neutrons. So the same number, so the mass number on the periodic table is actually going to be what we call a weighted average. Now, in any of your math classes, have you calculated weighted averages before? A little bit. It's actually how your grades work in most classes that have distinct categories, where it says 35% of your grade is your assignments and 25% of your grade is this. Those are actually just weighted averages, where you take those percentages and treat them kind of like a probability. And our atomic masses are weighted averages too. And one of the cool things about them is that the periodic table's atomic masses are actually unique to Earth. Earth has very specific distribution of isotopes. Other planets might have the same elements, but they're not going to have the same distribution of isotopes, what's called the natural abundance. So our periodic table works well for Earth, but we would actually need a different periodic table if we were doing this on a different planet or in a different solar system. I always find that that's kind of cool, where we're kind of looking at the actual fundamental pieces of the universe.
So is that why the atomic mass average is 35.45? Because it's more 35 than 37.
Correct. And the way we calculate this, so it helps if you have more sig figs than just 35.0 and 37.0, but it works well enough for us to show this. If we say that the mass of 35 is equal to, let's just call it 35, and the mass of 37 is equal to 37, if we want to know what the distribution is of these, we basically just do a quick algebra problem. Right, where we say, okay, well, I know that the average, the weighted average is 35.45. And that's equal to some probability that we can call, this is not an X, it's a Greek letter chi that gets used in chemistry. It means mole fraction. Or in other words, what's the probability that if you grabbed an atom at random, it's chlorine 35. So the mole fraction of chlorine 35 times the mass of chlorine 35 plus the mole fraction of chlorine 37 times the mass of 37. right? So, and there's a general form for this as well. Let's go through this for chlorine first, and then we'll expand it. But basically, for any atom or any element on the periodic table is going to have some version of this. If there's more than 2 isotopes commonly found on Earth, though, you might actually have 3 terms. If there's only 1 isotope commonly found on Earth, then you basically only have 1 term, and your chi is just 1. Right? In this case, though, if we want to know what these numbers are, we can start plugging stuff in. We know M35 is 35 within sig figs. We know M37 is 37 within sig figs. How can we figure these 2 out? We still have 2 variables to solve for. So I'm just going to plug in the 35 and the 37. We have an algebraic equation here now, right? How do we solve for these? We can't really isolate. I mean, we can isolate them. We can solve for this in terms of that. But if we actually want a number for this, anytime we have an algebra problem that has 2 variables, how can we solve for that? Substitution means we need another equation somewhere. If you have 2 variables, you need 2 equations. If you have 3 variables, you need 3 equations in order for substitution to work, right? So what else do we know about chi-35 and chi-37? Think about them like percentages.
Oh, chi-35 plus chi-37.
Yeah, if they were percentages, we'd say chi-35 plus chi-37 equals 100, right? These are just decimals, but they're a lot like percentages. So we can just say, we know chi-35 plus chi-37 equals 1. That's enough. That's our second algebraic expression, right? How could we plug it in?
We know that. Solve for one of them.
Solve for one of them over here and then plug it into the other expression, right? So let's just say we solve for chi-35 equals 1 minus chi-37. Again, if we were doing this with percentages, it would just be 100, right? We know that your percentages have to add up to 100. If we're talking about fractions, they have to add up to 1. So then that means we can say 35.45 equals 1 minus chi-37 times 35 plus chi-37 times 37. Is that something we can solve now? Subscripts make it look a little bit weird, but at least the chi kind of looks like an x, and you're used to solving for x, right? But algebra doesn't really change just because the variable is something besides an x. So distribute, combine like terms, and solve for chi-37. So we should get 35 minus 35 chi-37 plus 37 chi-37. And combine those. We get minus 2 chi-37 plus 2. Yep. Is equal to 0.45. We can solve that, right? So chi-37 is just going to be equal to 0.23, which means chi-35 is going to be equal to 1 minus that. So 70.77. Right, so if you're given the masses of the isotopes and the overall atomic mass, we can solve for these mole fractions or these natural abundances, or you can go the other route. Because like I said, not everything is going to have the same distribution of these. The mass of the individual isotopes is universal, but the distribution of the isotopes depends on where you got your sample. There are also lots of cases if you have who here's heard of enriched uranium? or enriching any particular element. Right? That's a pretty common term when you're talking about nuclear energy or weapons or anything like that. And when you enrich something, basically that means you're changing this natural abundance, usually so that you're making it so that the heavier isotope is more common than it normally would be. So if we enriched the chlorine sample, we might actually wind up with Chi-37 being 80% and Chi-35 being 0.2. Right, but so this is why we call it the natural abundance, and we are being specific. We're talking about natural abundance on Earth. All right. So one of the practice problems on here is an atomic mass problem like that for boron. It gives you the atomic mass and gives you two natural isotopes. It says find the natural abundance of each isotope. So basically exactly what we just did with different numbers. I guess before I turn you loose on this, the general form of writing atomic mass of any element looks a little intimidating. So I wanted to work this through with a simple one where we only have two isotopes before we brought this out, because mathematicians don't like to write a general form unless it can be applied to everything, right? And the general form means that we have to write it universally enough that it doesn't matter how many isotopes you might have. There's some elements on the periodic table that have 6 common isotopes on Earth, which means the general form of your equation is going to be the same, except you're going to have 6 masses times their abundance, 6 terms added together. Just like having extra categories in a class, right? If you have more categories, you have more things you have to add together at the end. So the way that the mathematicians do that is with a capital sigma. Has anybody seen this sigma notation before? We're not going to actually tackle it as, it's not going to be as bad as it is in math class, because this is just means you're going to add up all the pieces. Right? So basically you just take the percent abundance of an isotope times the mass of that isotope, and you add them all up for as many isotopes as you have. Right, so you might see this version of it written, but it just means the same thing we just did. This is the general form where you can make it as many terms as you need to. For the most part in this class, and most of the elements on the periodic table have 1, 2, or 3 common isotopes on Earth. There's not very many that have more than that. In fact, if you look at Wikipedia, another Wikipedia list. Can't go a whole lecture without referencing a Wikipedia list, right? And it's gonna open an image. Let's see, isotopes of chlorine. So this is also one reason why you don't trust the AI answers, because that doesn't tell you the whole story. You want isotopes of chlorine from Wikipedia, which does tell you the same thing, but says there's only 2 stable isotopes, chlorine 35 and chlorine 37. And look at that, we actually got pretty close to the right. We got 77% instead of 76%, but considering we were using really rough values for the masses, that's not half bad.
What would the third equation be for the systems of equations if you have 3 shared?
You need more information. So sometimes it'll be like the isotope 2 is twice as common as isotope 3 or something like that. So here's the Wikipedia list. Chlorine 37 and chlorine 35 are the only ones that are stable, though, that we really care about on Earth. These other ones can be made in particle accelerators and stuff like that, but we don't really consider them. So, and this is also a good place to get more sig figs on your masses. Look how many sig figs we have on each of these isotopes. We use 35 even, but it's really 34.968852, etc. Matson? It's basically you measure it and see if it gives off radiation, if it goes through a nuclear decay. Correct. And in fact, there are no stable isotopes of uranium, but there are some isotopes of uranium that have such a long half-life that we, for the most part, we treat them as though they're stable because their half-life is like 4 billion years. So on that time scale, yeah, it's radioactive. Yeah, it's decaying, but it's also stable in a lot of ways. And in those cases, the natural distribution of uranium in the samples we'll find on Earth is still going to be relatively constant because it's changing so slowly. In theory, it's not a constant though. If we measured the distribution, the atomic mass of uranium on Earth now compared to 1 billion years ago, we'd get different numbers. But that's a long enough time scale that we're not really worried about it. Diego?
How is the distribution like isotopes different off Earth?
The same reason that Jupiter has different elements on it than Saturn does. And both of those are different than Mars. Basically, when the solar system forms, it was just a cloud of gas, right? It was the result of a supernova from the previous star system. And as that gas all starts to coalesce into distinct rings and bands, you kind of wind up with certain weights of different elements being more common at certain radii from the middle. Based on how fast they were going, how heavy they are, etc. And so that means that you tend to gather certain elements, tend to gather more strongly together. That's the reason why there's no terrestrial planets past the asteroid belt, where it's all gas giants past that, because all the heavy stuff coalesced closer in the solar system. Yeah. I'm really glad you asked that because that's what we're going to talk about on Friday. We're going to talk about an electronic structure, which basically means the energy of different electrons we can actually measure by measuring what wavelengths of light get bounced off or absorbed. So we can actually look at distant stars and know what elements are in that star based on the light from that star. And we can do the same thing from our planets. We know that the sun has a certain spectrum of wavelength of light that it emits. And if we look at the light that comes from our sun and bounces off of Jupiter and then comes back to us, it's missing certain wavelengths of light because Jupiter absorbed those wavelengths of light. So based on what wavelengths of light are missing, we know what elements have to be on Jupiter. Exactly. Exactly. Yeah. Bryce, do you have a question? Then I see Ace.
So basically the universe just rolled panned a lot to sort of something.
Basically. What was written on the board when I walked in here today is a good first place to start. And I actually saw a science meme about this. The astronomer's periodic table is just helium and hydrogen, and then everything else gets considered a metal, and they don't care about it. Because the earliest star systems that formed were entirely hydrogen and helium. The fact that we have elements in our solar system that are not hydrogen and helium tells us that we're actually a second generation star system, because the only way that you got noticeable amounts of anything higher than lithium on the periodic table had to come from the fusion reactions of a previous star.
There's no like thoughts about school getting called later in the week. If we missed the Friday lecture, is there it's on the weekend?
So because you're off for a whole week, you're going to have another paper. We've got this practice assignment we're going to work on today and tomorrow. And then assuming we have school tomorrow. And then there's one more assignment that's just more practice counting protons, neutrons, and electrons, and a little bit more of this stuff that you'll do over the break. So if we miss lecture on Friday, it shouldn't be a big deal. All right. What else was there that we needed to go over before we could? Yeah. No, so just that a paper assignment. So thank you. So that the assignments, this assignment and the one that that for over the break are both going to be due a Friday of ski week. So a week from this Friday. So you'll have a week to, you'll have today and tomorrow in class, and anything you don't get done on this, you can work on over the break as well. And then just to keep it so it's you don't have a whole week without thinking about chemistry and don't forget everything, you'll have some simple problems like we've been doing, not like this one, like more the counting protons, neutrons, and electrons, that'll be due at the end of ski week as well. All right. Any other questions? I think this is all you really need to get started here. This is the challenge problem that I don't think I've ever had anybody solve right the first time. The challenge problem at the bottom here. It's a system of equations, and you can't just use the densities is the clue that I'll give you. You won't get the right answer if you just use the densities. You have to use the densities in conjunction with some other information. Other than that, let's pass these out, and then I'm just going to walk around and check in with you and practice getting your names right, and we'll work on these. There's more from the front. Yeah.
Thank you. I have no idea what
I think I figured out how to 115 pages.